Today we are going to discuss about tree search, that is searching for a node in a binary search tree. We should know what is a binary search tree. Binary search tree is a binary tree in which it contains some number of nodes. Every node contains a key and it follows certain rules. The first rule is the key in the left subtree should be less than the key in its parent value. See here, 15 is less than 20. 15 is in its left subtree. It is less than root value. That is first rule. Second rule is the key in the right subtree should be greater than the key in the parent value. So here root is parent, 25 is right child. So 25 is greater than 20. That is key in the right subtree is greater than its parent value. This is second condition. And again, left and right are binary search trees. So this is a binary search tree and this is a binary search tree. See, 15. 15 is root of left subtree. Its left value is less than root value. Its right value is greater than root value. Again here 25 and its left is 23, which is less than parent value. So everywhere the node in the left subtree is less than its parent value. The node in the right subtree is greater than its parent value. And next condition is duplicates are not allowed. There are no duplicate nodes in a binary search tree. Okay. Then what are the operations of binary search tree? We know that in any data structure, normal operations are insert, traverse, search, delete. Here also insert a node. We know how to insert a node into a binary search tree. Then traverse a binary tree. There are three traversal techniques. We can traverse a binary tree in three different forms: pre-order, in order, post order. We can traverse a binary search tree in three different orders: pre-order, in order, post order. Then search for a node. Now we are discussing about search for a node. We are searching for a target node. We are searching for a target node in a binary search tree. The other one is delete node. Now our concentration is to search for a node, searching a node in a binary search tree. That is tree search. Tree search is an important operation in binary search tree. In binary search tree, to search for the target, we first compare it with the key at the root of the tree. If it is the same, then the searching is finished. If it is not the same, we go to the left subtree or right subtree as appropriate and repeat the search in the subtree. For example, if we wanted to search for a target item 23, whether a node consisting of 23 is present in the binary tree or not, we are going to search. If it is present, it has to give us the position of the target value. If it is not there, it has to give us a message that the target is not found. Okay. Then initially we start comparing our target element with root value. We start comparing target value with root value. Is target equivalent to the key of root value p data? Suppose root is pointing to 20. We assume that a pointer p is now pointing to 20. Is p data equivalent to our target? What is p data? 20. Is target equivalent to p data? No, it is not the node we are searching. So we have to search either in left subtree or in right subtree, just like your binary search. It is a binary search tree. So we know that the values less than 20 we can get in left subtree. The values greater than 20 we can get in the right subtree. We are searching for 23. 23 is greater than 20. So we automatically understand that 23, if it is existing, it exists in the right subtree only. Then we go to right subtree. So we go to next right subtree of 20, right node of 20. Now we search, we compare. Is p data equivalent to 23? P data is 25. Is target equivalent to p data? No, target is 23. It is not equivalent to 25. So it has to compare. either left of 25 or right of 25. It is not having right node, but it is having left node. Whether it is available in the left node or not, we have to check. Because 23 is less than 25, there is a possibility of happening the 23, no 23 in the left subtree. So we go to left subtree, we go to left subtree, P is now pointing to 23. We compare P data is equivalent to key. What is target value? 23. Is P data equivalent to our target? Yes, it is. So position is assigned to P. Position is P. P is now pointing to 23. Position is P. P is our position of target node. P is our position of target node. In this way, we can search for a target element in a binary search tree. The same we implement using a function on an algorithm. Let me explain the function to search for a target node in a binary search tree. Figure shows a binary search tree. Binary search tree is a binary tree in which it contains some nodes. Every node contains key and it follows certain rules. The first rule is the key value in the left subtree should be less than the key value in the parent value. Second one is the key value in the right subtree should be greater than the key value in its parent value. Left and right are binary search trees. No duplicates are allowed. See here, 20 is root value. Left value is 15, it is less than root value. Right value is 25, it is greater than root value. Left is less than root, right is greater than root. Again, left and right are binary search trees. See at 15, 15 left is 10, less than 15. 15 right is 17, it is greater than 15. The same rule applies everywhere, right? So left value is less than parent value, right value is greater than parent value, left and right are again binary search trees, duplicates are not allowed. Our main operation in here is searching for a target element. We are going to search for 23. Target is 23. Means, is there any node with information 23 or not? If it is found, we have to get the position of the target element. If it is not found, we may get position as null. That too, we are going to search for target element using Treesearch function. Treesearch P target position. We are passing three parameters, formal parameters. Formal parameters. We pass three parameters. The first parameter is P. P is binary search tree. Binary search tree, here it is representing by root. Now it is P inside the function, it is P. Then target 23. We are going to search for a node with 23. Then position. We are going to find position, which is output. A pointer pointing to the target node if it is existing. If it exists, a position pointer has to point to the node, target node. If it is not found, position becomes null. Now, we start comparing with root node. Initially, if P is null, if there are no nodes, if P is null means if binary search tree is empty. If it is empty, sometimes binary search tree may become empty. If it is empty, there is no question of finding our target element. If it is empty, position is null. If it is not empty, then only we can search. If it is not empty, we can search. If it is not empty, we compare our target element with root value first. See here, if it is not empty, yes, it is not empty, it contains some number of nodes. If P data is equivalent to target, we start comparing our target element with root value. If P data, P is pointing to root, P is pointing to root node. Is P data is 20. 20, is it equivalent to 23? No, no, it is not equivalent to 23. So else part, else. Now we have to check. If target is not equivalent to P data, we have to search either in left subtree or in right subtree. We know that the left subtree contains values less than root value and right subtree has values greater than root value. Our target is greater than root value. So we compare or we search for our target element in the right subtree of binary search tree. If target, see 23 is greater than p data, if 23 is greater than p data, yes. So we continue our search in right subtree. We call the same tree search function because it is a recursive function where from here onwards we search in right subtree. Tree search p right target position. Now instead of p it becomes p right. Now p is pointing to its right. Now p is pointing to 25. It is now p. Now p is pointing to 25, not 25. Right side of p. P is p right. Then we are going to search for 23. We are going to check whether it is existing or not. If it is existing, we get the position. Otherwise, position becomes null. Now we again has to compare the entire the complete procedure again will be executing one by one from the first instruction. If p is null, p is 25, it is not null. Is p data equivalent to target? P data is 25. Is it equivalent to 23? No. Is it equivalent to 23? No. So else part is target 23 is greater than p data. P data is now 25. Is it greater than? No. Else. It is less than p data. Right? 23 is less than p data. So we have to search in left subtree. We call tree search function p left target position. We compare our target in the left subtree. Tree search in the left side of our target, our node. Then target is 23. We may find position. So P left. Now P is pointing to left subtree, left of P. Now P is pointing to 23. Now again the entire statements will get executed. If P is null, P is pointing to 23. Is it null? No, it is pointing to some node. Then is P data equivalent to target? P data is 23. Target is 23. Yes. P data is 23. Target is also 23. We had our target element. We found our target element. Now position is P. Position is pointing to P. Position is pointing to P. Now pointer position is pointing to P node. It returns, right? The value will get returned. In this way, we can search for a target element in a binary search tree. It is almost similar to our binary search. Our binary search, even in binary search also, the middle element is compared with our target element. If it is equal, we stop our searching. If it is not equal, we decide whether to search in the right side of the list or in the left side of the list. In the same fashion, in a binary search tree also, we compare our target element with the root value. If it is equal, we stop. If it is not equal, we repeat our search process either in left subtree or in right subtree. The process is repeated till we find our target element or we reach a null position. If it is null, position becomes null. If it is finding, if it is equivalent to a particular node, then the position of that node will be returned. Thank you.